Hello again, Tux Theater. This is the last talk of the day. Oh no. But looks like we've got something fun for you. We have Josh Bassett. And Josh is a FPGA hacker, coder, music producer, and retrofuturist. Z80 inside. Josh probably will not have time at the end for questions, but do send some through just in case there's time. Welcome, Josh. Over to you.
Thanks very much, and thanks to everyone for coming along to my talk. This is my second time speaking at Linux.conf, and I'm really happy to be back this year, this time in virtual form, coming to you from my garage here in the Byron Shire in northern New South Wales. So apologies in advance if there's any barking dogs or some old mate starts up a lawnmower or something like that. I guess we'll just deal with it. So if you watched my talk from last year, it was on how to write a retro arcade emulator, and this talk is kind of a bit of a spiritual successor to my previous talk, so yeah, let's go. So a bit about me. I go by the name Null Object on GitHub and Twitter and other places. I'm a software engineer by day, so my day job is working at the conversation, writing Ruby code, writing Scala code, working on back-end and front-end stuff for the Conversations content management system. They're based down in Melbourne, but I work remotely from home up here in northern New South Wales. I've been a hardware hacker for as long as I can remember, basically since I could hold the right end of a soldering iron. I guess you could call me a retrofuturist, so anything that's got a Z80 microprocessor or a Motorola 68000 microprocessor inside, you know, I'm pretty interested in playing around with that stuff. And in particular, lately I've been working on this project called Mr. So Mr is an FPGA platform for hardware preservation for old arcade machines, old computers, that kind of thing. I'll be talking a lot more about that later, but yeah, that's the intro, that's me. So an overview for this talk. In this talk, I'm going to take it a bit differently. I'm not going to assume that you know what an FPGA is, so I'll give a quick introduction to FPGAs. Then I'm going to talk about hardware description languages and how we can use them to describe hardware that you could run on an FPGA or on a custom chip. And then it's on to the real topic of this talk, which is Chisel. And Chisel's a kind of new hardware description language. So yeah. That's kind of the tofu and vegetables of this talk. And then finally, if there's time at the end, I'll be giving a bit of a code tour of some of the projects I've been working on and demoing, some of these arcade games that I've been restoring. So field programmable gate arrays, or FPGAs, what are these things? So they're not quite like a microcontroller, like an Arduino. And they're not really the same thing as a Raspberry Pi, which is a microcomputer. So what are they? So they can actually behave like either of these things, but they're definitely not the same thing. I like to think of an FPGA as this chip that has a sea of logic gates inside it. And you can configure those logic gates at runtime, so when you turn the FPGA on, using something called a bit stream, which kind of configures all those logic gates to become something. And this bit stream is not permanently flashed or anything onto the FPGA. So when you turn the power off, it kind of goes back to this amorphous sea of gates. And when you turn it on again, you need to reconfigure it. So that bit stream needs to be stored somewhere like in an EEPROM or in flash storage or something like that. And FPGAs can be used for everything from extremely simple logic all the way to, you know, very complex designs for things like CPUs, graphical processor units, you know, etc. The world's your oyster kind of when it comes to FPGAs and what you can do with them. And there's so many gadgets out there that have custom chips in them, and I'll guarantee you that like a lot of these gadgets with custom chips in them were prototyped. So those chips were probably prototyped on something like an FPGA. So they're really useful for prototyping things before you actually tape it out to a custom chip and stick it in your device. But sometimes it makes sense to actually ship a product with an FPGA inside it. So if the volume that you're running your product at is too low to justify, fabbing custom chips, because it costs a lot of money to actually manufacture chips. So if the volume's too low, then sometimes it just makes sense to ship a product with an actual FPGA inside it. And that actually has a nice benefit too. It allows you to fix hardware bugs after you've actually shipped the product. So you could, ship a new bit stream to your product, and the circuits would all just be reconfigured using your new bit stream. So if you want to get into playing around with FPGAs, it's not quite as simple as just like ordering one of these devices and plugging it into a breadboard or something. These devices are usually, they have very high pin counts, and they're usually quite complex devices in terms of power management and things like that. So you need to get your hands on a prototype board. And there's many of them out there, just like there's many, Raspberry Pi variants and many Arduino variants. There's many different ways you can prototype things using an FPGA. So the one that I'm most familiar with and I've been using a lot lately is this thing called the DE10 Nano. And it's powered by Intel, or Altera, who's now become Intel Cyclone 5 system on chip. And so that's this thing here. And it includes a dual-core ARM processor and a Cyclone 5 FPGA with about 110,000 logic elements on the same die, so on the same chip here, which gives you, quite a lot of options for the types of things you might want to implement on it. And I'll give you some examples of the things that I've been building on it later. So it's got some DDR3 memory, it's got an SD card under here, HDMI for
video
output, USB hosting, so if you want to plug peripherals into it, gigabit Ethernet, general purpose I/O here in these pin headers on the top and bottom. And I guess most importantly, the thing to point out here is that to develop bit streams for this device, you need to use a proprietary tool chain from Intel. You can get freely available ones, but it's not an open source piece of software. Here's another one from a big competitor, Xilinx, who was recently bought up by AMD. So they've got a system-on-chip Zinc device as well. So that includes an ARM processor and an FPGA on the same die. This time it's got slightly less logic elements. This one's got half as much DDR3 memory. So it's got SD card. It's got HDMI in and out, which is quite nice. So if you want to do video processing, like take a video stream in and do something with it on the FPGA and then send a video stream out again. This board's nice for doing that. And then same again, it's got USB hosting, gigabit Ethernet, analog audio, general purpose I/O. And the same deal with Xilinx. You need to use their own proprietary tool chain to make bit streams for this board. And then from the open source world, we've got this thing called the ULX3S from this makerspace in Croatia called Radiona. And they released the ULX3S recently. And that features a lattice FPGA with about 85,000 lookup tables. This thing's got SD-RAM on it, and not very much, about 32 megabytes. But the nice thing about SD-RAM is that it's quite low latency. So if you need to do things that require accurate timing, a little bit of SD-RAM goes a long way. And then same again, this thing's got most of the peripherals and things you'd expect. Interestingly, it's got this GPDI, so general purpose differential interface, instead of HDMI. It's kind of like the non-proprietary version of that interface. And you can do video and audio and Ethernet over that. And I guess the most important thing about this board is that you've got a completely open source tool chain available to you to develop software. Develop gateware for this FPGA. And yeah, that's quite nice, and it's growing more and more mature by the day. So how do you actually program circuits to run on these FPGAs? So the way that you do that is using something called a hardware description language, or HDL. So you might have seen circuits represented visually like this using something called a schematic diagram, and that depicts all the different elements of the circuit with the different wires and signals kind of interconnecting all those components. And that's nice because we can look at it and see how things all kind of fit together in the different parts like CPU and memory and so forth. But how do you actually convert something like that into a bit stream to put onto an FPGA? It's not quite so easy. So we actually use something called a HDL, or hardware description language, which lets us describe how the FPGA or custom chip, if we send the bit stream off to a factory to be manufactured. So we use the HDL to describe the circuit that's actually on these devices. And there's a few industry standards out there. They've been around for quite a while. So we've got HDL, Verilog, and System Verilog. You've probably heard of at least one of these. And yeah, like I mentioned, they've all been around since the early 1980s. System Verilog came a bit later, but yeah, they've been around for a while. And because they're industry standards and they've been taken up by so many manufacturers, these languages evolve quite slowly. So you don't see modern features added very often. And unfortunately, not all language features are supported uniformly by all the different manufacturers. So even though there's standards, those standards might not be implemented 100% across all the different synthesis tools. So firstly, VHDL, it's a bit of a mouthful, this acronym, Very High Speed Integrated Circuit Hardware Description Language, so an acronym for an acronym. It was developed by the Department of Defense in the early 1980s, and it's heavily inspired by the Ada programming language. And as I mentioned, this thing's an IEEE standard. The most interesting thing about VHDL is that it's a strongly typed language, and the compiler will complain if your types don't all kind of match up between modules. And it uses, when you're describing these circuits, use a hierarchical modular design. So kind of like Russian dolls, where you have like the top level design, and then within that, you've got kind of subsystems all the way down to the smallest components. Verilog and System Verilog, another flavor of hardware description language. Verilog was developed by a bunch of academics back in the early 80s, and this time it was inspired by the C programming language. So if you know C, you're going to feel pretty at home with Verilog. And the difference here is that Verilog uses type inference. So the compiler most of the time is going to make a best guess at what you're kind of doing when you're kind of sending signals around in your design, which can actually come back to bite you if you're not careful. Sometimes the compiler might make a best guess that doesn't make sense or you weren't quite expecting. System Verilog's a superset of Verilog that added extensions for kind of like system level synthesis and model testing, things like that. And again, you use a kind of hierarchical modular design when you're describing your circuits. So let's have a look at a few apples to apples comparisons just quickly. We'll go through VHDL, Verilog, and then I'll show you something in Chisel. So hang on, I'll just grab my highlighter here. Okay, so the first thing in VHDL, you need to import the standard libraries. So that's what's happening up the top here. Hopefully everyone can see that font size okay. And then we're going to describe a module. So in this case, we're calling it foobar. In VHDL, those things are called entities, but this is a module. And then we describe the inputs or outputs for that module. So those things are called ports. And so this module here takes a clock as an input, a reset as an input. We've got a data bus input, which is 8 bits wide. So that's what this bit vector type is here. And then we've got an output data bus that's also 8 bits wide. So those are the only inputs and outputs for that module. And then down here in the second block, we've got the architecture, which actually describes like the behavior of this module. And so within that block, we've got this process statement, and that defines another block inside it. So what's happening here is we're defining that clock and reset are part of what's called a sensitivity list. And anytime those signals changes, we kind of essentially reevaluate what's happening inside that block. So if the clock pulses or someone hits the reset button, then this stuff needs to be reevaluated. So the first thing that we're going to do is if it's reset, so if reset's asserted, that's like a truthy value, then we want to set the value 0 on the output. Otherwise, if we get a rising edge of the clock, then we want to set whatever's coming in on the data input to be on the data output. So in effect, we're latching the value coming on the input to the output on every clock pulse. Hopefully that makes sense. And this isn't meant to be a full description of the VHDL language. I'm just trying to give you a flavor. So the exact same thing in Verilog looks like this. So we've got the foobar module here. This time it's called a module. And we've got these inputs and outputs again. This time we actually need to explicitly state that this output here is registered. So with the VHDL example, it was an implicit register, which is sometimes confusing. You've just got to be mindful of the way you're using these signals. But here we need to actually declare it as a register. So that means every time the clock ticks or reset occurs, we're going to update the value of that register. And then so again, if reset's asserted, we clear the value of that register. Otherwise, we just latch whatever's coming in on the input. Makes sense? Let's move on to Chisel now. So this is what the same thing looks like in Chisel. So we've got to import Chisel standard library first up. And Chisel actually is it's a domain-specific language, so a DSL that's built inside of Scala. So if you've ever written Scala or seen Scala language, this might look a bit familiar to you. And so to build modules, we're actually relying on Scala's type system, so defining classes and so forth. So in this case, to make a module, we declare a class called foobar, and we extend from the Chisel module superclass. And then same thing again, we're defining IOs here. So, this is our input data bus, this is our output data bus, and we're just going to infer the width of those things. Those are bit vectors, so, a bunch of signals all being carried together. And then the registering part of it, we just use this register function call, so regnext. That means on the clock tick, we're just going to latch that value into the register. And this is the second parameter here is what happens on initialization. So when the circuit starts up, what's the value of that register? And then we're just assigning that to the output. And so this behavior is exactly the same as the two things that you've seen before. And the nice thing about Chisel is that you actually don't have to declare modules for really simple things like this. You can just do like a function call in a one-liner like this. This is exactly the same behavior. And I guess one thing to point out here, and you might have noticed, is there's no mention of the reset or clock signals. That's because Chisel makes these particular signals implicit for all modules. So you've got an implicit clock and an implicit reset, and you don't have to continually pass them around between modules unless you actually want to override the default clock and reset. So I'll come back to that later. All right, so that was a brief intro to Chisel. Let's just talk about what it is. So as I mentioned, it's a HDL for describing circuits using Scala. And it leverages these advanced features of a modern language like Scala. So the type system, as you saw before, there's other things you can do to kind of lean more heavily on Scala language to describe circuits. It's an open source project from UC Berkeley, and it's been around since around 2012. And it allows hardware and hardware generators to be described using code. So hardware is pretty obvious, but a hardware generator, that's actually something that describes hardware itself. So I guess a good example here, it might be if we're talking about a CPU, we might have an instruction set for a CPU described somewhere like in a document or in code or whatever. And we can use a hardware generator to generate hardware from that actual description, which is really useful for doing things like maybe you want to build a compiler and design a chip at the same time using a hardware generator. So it's a bit meta, but it's quite powerful. Who's using Chisel? So Chisel is currently under the CHIPS Alliance, which is part of the Linux Foundation. The CHIPS Alliance implemented an open source RISC-V processor core using Chisel. It's called Rocketchip. It's quite good. Google has developed something called an edge tensor processing unit, TPU. This is an artificial intelligence accelerator chip. And they actually turned this into a physical chip. And there's a really good YouTube talk by the engineers that worked on this project, just talking about Chisel and kind of the pitfalls and gains, just interesting kind of analysis on using Chisel in such a large scale project. And there's a growing list of industry partners and projects and libraries out there. So under the CHIPS Alliance, not all these people use Chisel, but this is kind of CHIPS Alliance hosts Chisel, and you may have heard of some of these companies before. Why is Chisel interesting? I mean, this is just my opinion, but I think high-level hardware design is really important. So if you're a software engineer, you don't sit around coding and assembly all day unless you're writing software for microcontrollers or something like that. So we typically use a much higher level language to do these things. And so same with hardware. I think you can kind of get a lot of benefits out of using a high level language when you're designing hardware. As I mentioned before, you've got these implicit clock and reset signals using Scala implicits, which may not sound like much, but not having to pass a whole class of signals around in your code is very nice. And because it's based on Scala, you get to use all of Scala's testing libraries and rely on these modern software engineering best practices that if you're a software engineer, you've kind of come to rely on in modern times. So things like unit testing and CI, that's all possible using Chisel. And I think most importantly, it allows you to move fast and spend less time debugging on actual hardware. So the more time that you can spend writing circuits and verifying them kind of in the same space, so not having to not having to make a bit stream and run it out onto an FPGA. That kind of keeps your iteration loop very fast. So this whole kind of red-green refactor mantra you can replicate in hardware land. And for some big designs, synthesizing out to a bit stream for an FPGA can take, minutes or hours. So the faster you can keep this loop, the better. And I kind of, there's a little wink face here, but, IntelliJ is an IDE for, Java-like languages, but they've got flavors for all different programming languages. But because, you're kind of moving out of the hardware space and more into the software engineering space, you can rely on tools like that quite heavily. So just a quick example here, but, for Xilinx chips, this is what the free and proprietary software tool called Vivado looks like. The text editing here kind of is like something out of the 1990s or early 2000s. It doesn't quite have all the same kind of things that you'd come to expect from a modern IDE. And same for Quartus, which is the Intel tools. It's great for kind of synthesizing circuits and debugging, but the programming experience isn't great. And just as a comparison, if you're using something like IntelliJ, firstly, it's free and open source, but all these things like syntax highlighting, syntax checking, style checking, static analysis, that's all really important and lets you move in quite an agile way. Also things like inline documentation, browsing and navigating your code, refactoring tools, so things that you might actually have been scared to tackle, like big refactorings, in other environments, you can just kind of take on with ease. And things like Vim mode as well, like I'd put that just as a bit of a joke, but the more comfortable you are with your tools, the faster you're going to be able to work. So I think it's really important. All right, so let's just have a look at some of the Chisel fundamentals, and then I'll get on to demoing some stuff. So in Chisel, we've got primitives, so primitive types like bools and bit vectors, unsigned and signed integers. This is the way that you express those. So this is the way you define a type. You give it, a width, so 16.w, that's a 16-bit wide unsigned integer. And if you want to create a literal value, then you use this kind of syntax. So for example, 1.u is an unsigned integer, 8.w means it's 8 bits wide. So you can kind of, in a concise way, express your types and primitive values. So logic kind of works much the same way as you'd expect in a software language, except this time, you've just got to keep in mind that the thing that's actually getting created is hardware gates on, a physical chip. But all the basic logic stuff's there, like and or not, all those kinds of logic gates. Arithmetic, all that stuff's there as well. So subtraction, addition, multiplication, and division. The one thing I will point out is they've got these extra kind of operators for expanding, an expanding addition. So that means like if you add 1 to an 8-bit value, then it will expand into a 9-bit value, which means that it won't overflow. You'll be able to capture the full resolution of the addition, which is a nice addition to the language. And then you've got these things called wires, which represent, the signals interconnecting things. So a wire is always of a type. So here we've got an 8-bit unsigned integer wire, and then we're assigning the value 1 to that wire. Or you can do it all in one line with wire in it. and then giving it the literal inside there. And then later on, you can say, you know, if some conditions met, then change the value of that wire to something else. So here we're setting it to 2. Registers are kind of, you know, one of the fundamental building blocks of sequential circuits. So, you know, the ability to latch a value on a clock pulse. And the way that you define registers in Chisel is using the reg function and then, you know, the type of the thing that you're latching. So here we've got like a Boolean value being latched, and it's latched on a clock pulse, but the clock is actually implicit. So you don't have to keep passing around that clock as a signal to tell registers when to latch. And then you can assign initial values, and then, you know, later on when some conditions met, change the value of that register, and that will be updated on the next clock pulse. We've got these things called multiplexers. So this is another one of these fundamental building blocks. So it's a pretty simple thing. It takes 2 values, A and B, and then has one output Y. And then this select line here, that just chooses whether on the output you've got A or you've got B. It's as simple as that. And so these things are called muxes, and you just call the mux function and pass those signals in, and it will choose the value based on the selector value here. That's a way of like explicitly defining a mux, but here you can implicitly define a mux by assigning a value and then, you know, having a condition and change the value later on in the code. That defines a mux as well. Counters are another one of these building blocks. So, you know, you have a value, and then every time the clock pulses, you add 1 to that value. So here's a counter from 0 to 255, and then that's assigned to Q, and that'll just like count up through numbers. And then when Q gets up to 255, this wrap signal gets asserted. And that's really useful for all different types of circuits. State machines are another one. So like here we've got a traffic light. So it goes from red to orange to green. So we define the states. We have a register that stores the current state of the traffic light. And then depending on the previous state, you know, we update to the next state. So when the traffic light's red, we go to orange and so forth. Bundles are a way of passing a group of signals around together. So, you know, this is from my arcade work. So we've got all these analog video signals here, and we always want to be passing those around as a group together. We never want to kind of pass them individually. So a bundle is a way of like grouping those signals together. And then, you know, just like with a wire, with any other type, you can create a wire which has an instance of that bundle and then assign those signals. And then the syntax is quite nice for passing that bundle around. So if you've got like another module that takes the video signals using these like greater than, less than operator here, you can just like assign all of those signals together at once, which is really handy. You might see that in my code demo a bit later. And vectors are kind of like arrays in programming. So we've got like a fixed number of a particular type of values and storing them in a vector. So we've got like this queue structure here, and then we can assign values to the different indexes of that queue. Otherwise, we can just like do it all in one go and initialize the vector with those values. And then the way you get the values out of that vector is like either by using the index notation here, or you can use like list head and tail notation to get like the head or the tail of the list, which is similar to the way you do it in software. Modules are the way you kind of tie all these things together. So, you know, you've got some signals, some behavior. You want to kind of wrap that up into one piece of functionality. I won't spend too much time on this, but yeah, you've got inputs, outputs, and then your behavior. And then the way that you instantiate a module is by calling this module function and giving it an instance of that class. And so here the adder adds, you know, 1 and 2 and gives you 3 as an 8-bit vector output. And then parameters are a way of kind of generalizing some of that behavior. So rather than like, you know, hard coding this module to 8 bits, we can just pass in a parameter when we instantiate that module. So this becomes a 4-bit wide unsigned integer adder now. So the output is still 3, but the result is a 4-bit wide unsigned integer. And then finally, we've got these things called black boxes, which are a way of kind of wrapping up functionality in some external module that may be written in, say, you know, Verilog or VHDL or some other module that you've gotten from somewhere. You want to bring that into Chisel land. You use a black box to do that. And so the only difference here is that you need to explicitly define a clock and reset, because Chisel doesn't know how to kind of implicitly pass those things onto an external module. But otherwise it works in the same way. You just have your inputs and outputs. And then, there's syntax for specifying the name of the module if it can't infer it automatically. Right, so MR is this project that I've been working on for, I guess, over 12 months now, developing these FPGA cores. And the latest one that I did was using Chisel, mainly because I was interested in Chisel, but also I felt like it was a really productive way to tackle these kind of larger systems. So MR is based on this D10 Nano prototype board that I showed you earlier. And this is it here in the middle, sandwiched between these two other boards. And that's actually from a company called Terrasix. So it's not open hardware, but all of the additional kind of bits of the platform that people have designed, these are all open hardware modules that kind of stack onto this thing to build it up into a platform. So we've got like analog I/O here, down the bottom's like a USB hub thing, SD-RAM over here. And the name has nothing to do with gender. This is a successor to something called the MIST project, which is why it's kind of capitalized a bit funny. Yeah, so this is based on something that came earlier, custom board, and then MR moved on to this university subsidized educational board because the cost to performance is just kind of unmatched at the moment. That's the only reason that it hasn't been moved over to open hardware. And so, yeah, everything about it, apart from this board, is open source. So all the hardware modules, the framework that it all runs on, and the FPGA cores that people are writing. And those cores are for arcade games from the 80s and 90s, other retro hardware like Amiga 500, Atari ST, that kind of thing. And yeah, I've been kind of focused on the arcade preservation side of this. So implementing old arcade games to run on this platform. And if you want to check any of that out, the project's under MrDevel on GitHub or mrfpga.org. And I guess I'll give it a quick demo of the latest core that I was working on. So it's this game from 1987 called Dodonpachi. If we could bring that up now in the video feed. Yep, so this is running entirely on the MR, and it's all described in Chisel. Yeah, and so this is like a running version of the original game using the original arcade ROMs and all that kind of thing. So it's like I don't know, there's arguments about whether this is emulation or this is the real thing, but it's a hardware description of the original arcade hardware. And yeah, I guess I've been working on this project for about 8 months, and there's a lot of, these kinds of games have big cult followings, so there's a lot of interest in some of these arcade games on Facebook and Twitter and other forums. There's a lot of people following this work, and yeah, it's great. I mean, we're kind of getting up to the point where we can implement, late 90s hardware. So, there's quite a lot of moving parts in a thing like this. I'll just hold up the circuit board for one of these games, but you can see there that there's actually quite a lot going on. Like we've got the, hang on, this is back to front. We've got the Motorola 68000 processor and some like custom GPUs and memory and all kinds of stuff going on here. It's not a simple thing. It's basically like a custom computer just for running that game. And so, reverse engineering these games is quite a process and quite a challenge, but yeah, it's a lot of fun. So I'll see how much time I've got left, and maybe we'll do a bit of a code tour. And I'll just show you kind of what the Chisel implementation for parts of this game look like. If you can just switch over to that. Okay, so you can see my text editor there. Hopefully the text is big enough for you to read. I can zoom that in a bit more. So this is all Chisel, and it's defined in modules. So this cave module is kind of the top level module for running that arcade board I just showed you before. And so within that, we've got all the stuff that I was showing you before. We've got these inputs and outputs in the I/O bundle. So I've got a couple of clock domains here. So there's a few different clocks that run that game. There's different signals that happen, vertical blank and frame ready. All this stuff is just like getting passed into this main module. They've got things like, a bundle for the joystick and, stuff for memory. So these ROMs that store the sounds and the program data, tile data. And then we've got like audio outputs, frame buffers, all that kind of stuff. So hopefully that looks more familiar to you now. And then, there's so much here, but I guess the things that I want to point out are the kind of where I'm leaning more heavily on Scala language. So I've built little DSLs for describing parts of this hardware. So here I'm defining the memory map. And, to do this in another HDL like, Verilog or VHDL could actually be quite a lot of code. And it could be quite convoluted, but, kind of leaning on Scala and using a little mini DSL that I built, I can define the memory map for the whole system. So, from this address to that address is, the program ROMs, and from, this space is the main RAM, and so on. And it's quite human readable, and it's also, I can go in and debug things quite easily because I can just like see what's happening. That's quite nice. I really enjoyed that about Chisel. And then the other thing I mentioned was, being able to use bundles to pass around all these signals together is a huge win. So not having to pass all these individual signals around, I can just like pass them as a bundle. Fantastic. It lets me move so much faster and makes the code so much more readable. And I've only got 5 minutes left, but the last thing I wanted to demo was just how you run unit tests. So I've got a whole bunch of tests written for all of these different modules. And this is IntelliJ, so I can just like kick off a test run for, the util module. And I don't know if you can read that. Hang on, I'll try and bump the font up. But you can see, it's just running through a bunch of tests that I've got written. And I can click through to those tests if, those are failing. And this is all kind of using Scala testing libraries. So there's plenty of good documentation on how all this stuff works. And, you're just kind of creating instances of those hardware modules and then saying that you expect, poking signals and then expecting output values. And you don't have to synthesize that onto an FPGA. I can just run all that stuff in IntelliJ, and it lets me kind of move fairly quickly with a great deal of confidence. Yeah, it's quite nice. So let's switch back to my slides for just the closing remarks. All right, so if you're interested in Chisel and you want to learn some more, there's this great book by Martin Schuberl. He's from, I think, a Denmark university. I've got a note here somewhere. Anyway, he's an academic and he wrote this great book on Chisel, and I totally recommend it. There's free versions of it, or you can buy a paper copy. I learned a great deal from this book. And there's also a Chisel boot camp set up if you want to kind of step through some examples. And yeah, University of Denmark. And there's lab material. So he's got like a whole course in digital electronics done in Chisel. So, you're free to kind of go along and do some of those labs and read the documentation that he's put together for that course as well. So that's it. Thank you very much. And I hope you enjoyed the talk. And yeah, it's been interesting doing it virtually. Hopefully it worked out from my garage here. Thanks a lot.
Thank you, Josh. That was a lot of fun. I think you got
okay,
you got a
my
good
pleasure.
end of day. Everybody enjoyed the demo there.
Fantastic.
We do have a couple questions and we have a couple minutes, so you can fit at least one of them in.
Perfect. Let's do it.
Our first question is, are there good open tools to output Chisel designs to other languages, such as those you described at the start of the talk? For example, if you have to get some design fabricated or passed on to other teams that only use others.
Right, yeah. So Chisel outputs to Verilog by default. They're looking at output for, VHDL as well, but Verilog's kind of the main output engine. And the output in Verilog is not totally human readable, but you can definitely run it in signal tap or something like that and not be totally confused if you name all your signals properly. So yeah, you can definitely integrate this into other projects that have hardware written in other HDLs.
Great. There are some more questions, but I might stop it there so that we can wrap up in time. Everyone, you can head over to the Tux Theater post Talk Q&A chat channel in Venulus to have a chat to Josh, ask the rest of the questions. I'll paste the questions we didn't have time for into that channel so that Josh can see them. But remember, the conference closing starts at 5:40 Melbourne time. You don't want to miss that. So better get those questions in quick. Thank you again, Josh, for such
Thanks
a good,
very much.
fun and great talk.
It. Fantastic. All
Bye.
right. See you, everyone. Bye.